Hello and welcome to your Wednesday review for Khan Academy. Average rate of change, graphs and tables. What does the average rate of change mean? When you hear the phrase, it may you may have an association with slope. Well, what does that mean? I think it's easiest to understand if you understand it in the context of a function. So let's make up a function that does something like this. And let's consider the average rate of change from the salmon point to the green point. So as I'm looking at the blue curve traveling from the salmon point to the green point, I notice that the curve is going down first. So if I'm thinking about what's happening, and the slope, if you think of slope as the behavior of the function as the function passes from left to right. In this case, the function is going down, so it's got a negative slope, and then it's kind of flat, so it's got a slope of about 0, and then it's going up shallow, and it's got a slightly positive slope, and then it gets steeper and steeper, and it has a bigger and bigger positive slope. It's going up faster and faster. The change over time, the change as x changes, as your x coordinate changes, g is going up faster and faster. So how do you average that out? Average out that behavior, going down, going flat, going up a little bit, going up steep. Well, you look at the straight line from the pink. Let's try that a little more straight. The straight line from the pink point to the green point. And if you can find the slope of that line, that would be the average slope of the function from the salmon point to the green point. And what do you use to get that? Well, if you know the coordinates of the salmon point and the coordinates of the green point, you can just plug it into the slope formula. And to help you remember the slope formula, it's the change in y divided by the change in x. So when we look at these multiple choice options and consider, we want to look for examples where the change in y divided by the change in x is 0. And what would need to happen for the change in y divided by the change in x to be 0? Well, I can't have 0 in the denominator. That can't be 0. Can't be 0. So the place where I need a 0 is in the numerator. If I want the answer to be 0, the numerator must be 0. In other words, the y values can't change if I'm going to have an average rate of change of 0. And so when I look at 1 to 3, if I look at the point 1 to 3, I see that, in fact, in this case, my function at 1 is at -3, and at 3 is at 3, and so I have a clearly positive slope. So that is not a slope of 0. And now I consider B, where I have a range from 0 to 4. At 0, my function's at -2. At 4, my function's at 6. And if I plot those points, I get -2 at 0 and 6 at 4. Again, a positive slope. Can't be that either. Finally, well, not finally, I still got 2 left. Next, I I consider C, where I have a range from -2 to 2. At -2, the function is at 1. At 2, the function is at 1. What does that look like when I graph it? At -2, we're at 1. At 2, we're at 1. And what has to happen between there? Well, we don't know what happens all the way between there. It might do all sorts of funny things. It might move all over the place and do a lot of complicated things. But at the end, it gets to the green point. And it starts at the salmon point. And if we're averaging the behavior across that interval, you could see that the slope is 0. So there's our answer, C. Next problem, average rate of change word problems. Now we're wrapping the same concept up inside a word problem. And using the same reasoning, we're going to look here. Aiden is a spice trader. The price he charges for an order of cumin in dollars as a function of the size of the order in kilograms is graphed. What is the approximate average rate? There we go. Slope again. At which the total cost increases as the order size increases. So again, we're going as the order size increases, as we're increasing cumin, as we're going from left to right on X, what happens to Y? What happens to Y? So we're increasing from 100 to 600, and we're trying to find out what happens to the total cost over that interval. So if we look here, we see that point, the point corresponding to an X value of 100, is somewhere between 400 and 500, right? That's 500, about halfway between, so we'll put 450. An estimate is appropriate because it does say right here the approximate average rate. And over here at 600, we're at, again, about halfway between 1600 and 1700, or maybe 1650. So now how do we find out the average rate of change? Well, we consider the line that I just drew, the green line that I just added. We consider the slope of that green line, and to find that slope, we just plug into the slope formula. y2 minus y1 over x2 minus x1, and we see what the average change in y is over the average change in x. So we take that difference, right, from 1650 to 450, that's y2 minus y1, over the change in x, that's 600, 100 to 600, or 600 minus 100. And plugging that into the calculator or doing some simplifying, you get not approximately, you get actually exactly 2.4, which is answer choice D. Okay, how do you approach this problem? Several different ways to approach it, but I think the easiest is to really utilize the information that we've built some comfort with. We've started to recognize that constant term as constant, which means that if I plug 0 in for x, we're left with just 7. These terms turn to 0, right, when x is 0. So in other words, 0, 7 is a solution, which means it's on the graph. So we look at A, and yeah, that's got 0, 7 right there. B, 0, 7 is on there. C, 0, 7. D, does not have 0, 7, no point, so we can eliminate D without doing any real calculation. Another thing to notice, the coefficient of x squared, 4, is a positive number. It means it should be a parabola pointing up. Works for B, works for C, but not for A. Okay, so now we've narrowed down our work to just graphs B and C to determine which of those is the appropriate fit. We can look at a couple of points and use our equation, our function definition, as a point tester. So test a point. And to test the point, we need to determine the coordinates of the point. This point is at x is 1 and y is 3. So we can plug that in, put the 3 for the y, and check to see if that equals 4 times 1 squared plus 8 times 1 plus 7. I'm adding together a bunch of positive numbers on the right that are all bigger than 7. It's clearly not going to work, but just for completeness sake, 3, and now I've got 4 plus 8 is 12 plus 7, 19. 3 is not equal to 19. Cannot be C. B has to be our answer. You could plug -1 into the function to check and confirm, but I feel confident enough about our methods that we're going to move on. Expanding a polynomial, getting rid of these parentheses. We're going to see in class that this particular situation, when you have two terms times two terms like that, a binomial times a binomial, that that expands to AC plus AD plus BC plus BD. And we're going to call this FOIL. And we're going to take some time to prove that this is true because, right, in answer, question might be, why does it work? Why do I get to do that? Why can I just go from there to there? Why does it work? We're going to see that it's true because of the distributive property. And the distributive property does not tell us directly how to deal with this situation. The distributive property says you have something like this, and it's equal to something like this, right? Where you've got a number multiplied by a sum in parentheses is equal to the number times the first part of the sum plus the number times the second part of the sum. That's not exactly what we have here. To do this, we're going to use some careful reasoning. To write this, to prove, we're going to do some careful reasoning. I'm not going to go over that reasoning right now. I'm going to save that for class, but I'm going to hint at it a little bit as we do this. And mostly, I'm going to approach this in the calculation mindset, not in the understanding why it works mindset. Those are two really different frames, and both are essential for mathematics, key parts of doing mathematics. We're going to focus on the calculation part right now. In class, we'll go back and try and answer the why does it work. So the observation that I do want to make, and this is not strictly necessary, but I think it's useful to see, and it'll help us when we're trying to do this later. R squared minus 7, I can distribute that inside the parentheses here. And when I distribute it, I'm taking this r squared minus 7 and this thing inside the pink rectangle, and I'm multiplying it by each of the terms. So I'm going to end up with negative r squared times the thing in the pink rectangle, r squared minus 7. And what am I going to do then? Well, I'm going to distribute that negative r squared. And so that negative r squared is going to multiply by the r squared and by the negative 7. And the same thing will happen with the 3r. And the same thing will happen with the negative 7. In other words, each of the pairs of terms, each of the pairs that exist in this system will be multiplied. Each of the pairs where one of the terms is from the first uh, polynomial, and the other term is from the second polynomial. Okay, so let's do this then. So we're going to take this negative r squared, and we're going to ensure that we multiply this by both of these terms here. Negative r squared times r squared. What's that? Well, I'm not sure, but let's just write it down. Negative r squared times negative 7. Negative times a negative is a positive, and then I just have 7r squared. Okay, and now focusing on the 3r and distributing that. 3r times r squared. What's that? I'm not sure, but I'm going to write it down. I am actually sure. Just play along with me. 3r times negative 7. 3 times negative 7 is negative 21 times r. And then we have the negative 7 to multiply by each of the terms. Negative 7 times r squared is negative 7r squared. Negative 7 times negative 7 is plus 49. So this expression is equal to this whole thing here. Now we can simplify. We can notice, first of all, that r squared times r squared is really the same. What's r squared? It's just r times r. And so we have r times r, which is 4 r's, r to the 4th. And so we can put that down as our value here. Negative r to the 4th. And move on. And you might notice 7r squared and 7r squared, 7 plus and 7 negative. Those cancel. And then we have 3r times r squared. Again, we have an r times an r times an r. So that's r cubed. And minus 21r. And finally, the plus 49. And there is our answer. Factoring completely. So how do I factor this? Well, the basic technique to factoring when the leading coefficient is not equal to 1 is to take that leading coefficient, that 8, and multiply it by this number here. So I get 8 times negative 5. 8 times negative 5, which is negative 40. And then to consider all the factors of negative 40, we're doing the technique called grouping here. We're going to consider all the factors of negative 40, and we're going to find the special factors that add up to negative 18. So what are the factors of negative 40? Well, first of all, I have negative 1 and 40. But if I'm multiplying together to get negative 40, I could do it the other way as well. I could be 1 and negative 40. Okay, I could have done 2, negative 2, and 20. And similarly, you could have 2 and negative 20. 3 times 13 is almost 40, but there's not an integer that I can multiply 3 by to get 40, so 3 isn't a factor. Then I move on to 4. 4 times 10 is negative 40, so negative 4 and 10 gives me negative 40. And I could do the other one, 4 and negative 10. Continuing on, 5. 5 times 8 is negative 40. We see up here, negative 5 times 8. Or, again, 5 times negative 8. And now I think about 6. 6 times what gives me negative 40 is a little more than 6, but not 7. And at this point, I'm gonna reach values in the first position that are already higher than the values in the second position. So I know I'm kind of done. I've tried all the values that are worth trying. I've found all my factors. And I'm going to look at each of these factors and I'm going to consider the sum, and I'm going to think, is it equal to negative 18? Negative 1 plus 40 is 39. Negative 2 plus 20 is 18. Negative 4 plus 10 is 6. Negative 5 plus 8 is 3. All positive. None of them equal to negative 18. Negative, so I move on to the other side. Negative 1 and 40 is negative 39. Okay, well, I got a negative number at least. 2 plus negative 20, there we go. There's our negative 18. I can stop at that point. I've found my pair of factors, 2 and negative 20. And here's what you do. Once you've found this pair of factors, 2 and negative 20, we're going to rewrite this term here because we know that negative 18 is the same as negative 20 plus 2, right? But we're talking about x's, so I got to stick an x in there. And I'm going to rewrite this entire expression replacing the negative 18 with negative 20 plus 2. And what I do now is I look at the first pair of terms and the second pair of terms, and I factor out the greatest common factor from each. 8 and 20. What's the greatest common factor of 8 and 20? It is 4. So I can factor a 4 out. But then I also notice that there's an x here and an x here, x squared and an x. And so I could factor out more than the 4. I could factor out an x as well, leaving 2x minus 5. And how do I confirm that? I just immediately distribute the 4x in my head to undo that distributive property application. 4x times 2x, 8x squared, it checks out. 4x times negative 5, negative 20x, it checks out. I successfully factored. Now I look over here, and you might notice already this 2x minus 5. It matches up exactly with this 2x minus 5. The way we're going to write this, just to make it pop out a little more, is we're going to write 1 times 2x minus 5. Where'd that 1 come from? Remember what we were doing? That was just like the 4x. That was the greatest common factor of 2x and negative 5. 1 was. When we write it like that, again, we see that we've got our orange or salmon rectangle and our salmon rectangle are repeated quantities. And it's like we're saying, just an example, different situation. It's like we're saying we've got A times a blue rectangle plus B times a blue rectangle. Well, the distributive property says that I can take that blue rectangle and pull it out to the front. And I could write that as blue rectangle times, and then put it in parentheses, the A plus B. And you can see that those two have to be equal to each other because all you do is distribute the blue rectangle to get back from here to here. Right? We're going to use the same idea here. We're going to take that salmon rectangle and factor both of them to the front. And so we're going to write 2x minus 5 times, and what's left over? Well, we've got a 4x from the first term and a 1 from the second term. And we've pulled our pink rectangle or salmon rectangle to the front. There we go. And it's our answer. And we're done with the problem. You could check it by distributing like we did on the previous problem here. Okay, solve for x. Enter the solutions from least to greatest. So we're going to rewrite this expression, replacing the expanded trinomial, the three terms, with a factored form. We're going to look at that negative 10 and we're going to find factors of negative 10 that add up to 3. What are my factors of negative 10? Negative 1 and 10, or 1 and negative 10, negative 2 and 5, or 2 and negative 5. And that's it. So I've only got 4 terms to consider. And when I add them up, I get 11. Wow, sad. 10 plus negative 1, I get 9. 3, negative 9, and negative 3. And if I look here, I see that I want a positive 3. And since the leading coefficient is 1, I actually don't need to do the same steps that I did in the previous problem. I can just more easily go directly to the factored form using the coefficients that add to 3. What adds to 3? 5 and negative 2. And I could just write it like this with my negative 2 coming down and my 5 coming down. Great question, you might ask. Why does that work to factor like that? Fortunately, for this one, we will take the time to carefully go through and explore why that technique works. It's going to involve carefully working backwards from the answer we know we get to figure out why we get it. See if you can do it before we get to it as a class. So what situation do we have here? Well, the key thing to observe is that we have a number, x minus 2 is a number, and we're multiplying by another number. X plus 5 is another number. We're multiplying two numbers together to get 0. What does that tell you? Well, the zero product property tells us that either the first number, x minus 2, is 0, or the second number, x plus 5, is 0. Again, the reason why, we're multiplying two numbers together and we're getting 0. How can that happen? There's no numbers other than 0 that you can multiply together to get 0. One of those numbers has to be 0. That's all we're saying in this step here. We're just saying either the first number, this thing, has to be 0, or this one has to be 0. Okay, well, if x minus 2 is 0, then x is 2. If x plus 5 is 0, then x is negative 5. And we've got our solutions. And carefully, lesser, which one is less, 2 or negative 5? Negative 5 is lesser, so you put that there. And then 2, oops, uh-oh. Kind of fun. Trying to make it like a little hop over the top there. Kind of looks like that. Not quite. I don't know. Keep working on it, getting used to this device. 2 goes here, and the negative 5 here. Final problem. Final problem. Just wanted to check. I'm getting burnt out. Second time I've had to record this because I forgot to have the camera on. Um, how do we approach this? Well, hopefully you notice 2 is an even number, 12 is an even number, and 18 is an even number. I've got 3 terms, all of which are even, and I've got an equation. Well, I can multiply both sides of the equation by 1/2, or divide both sides by 2. And when I do that, I know that I'm producing another equation that's an equivalent equation to the first one. And what's true about equivalent equations? They have the same solutions. So if I solve this thing, whatever the solution is, will also be a solution to this thing. That's convenient because this one, even though it looks more complicated, is going to be easier. Again, I distribute the 1/2 to each of the three terms, and I get 1/2 times 2 is just 1. Minus 6x plus 9 equals 0 times 1/2 is just 0. I have an expression with my leading coefficient, the number in front of the x squared. What can I put there without changing the value? If I put a 0, 0 times x squared, the x squared would disappear. If I put a 2, well, 2 times x squared is different from just x squared. The only thing I can put there without changing the value is a 1. The leading coefficient is 1, which means I can use the more straightforward factoring technique. Just look for factors of 9 that add up to -6. Factors of 9, 3 and 3, or -3 and -3, or 1 and 9, or -1 and -9. And -3 and -3 is the pair that sums to -6. So I just write down the kind of structure that I'm going for, where I know that the terms, the first two terms are both x. That's how I'm going to create that 1x squared. And then I pull these values over and I have a -3 and a -3. So I have a number, x minus 3, times another number, the same number equals 0. So that number has to be 0. So x is 3 and we're done. Enjoy your Wednesday.